let me provide a little bit of guidance, and purposely I'm also going to not kind of give everything. There is a x minus 6 in the denominator. As we hopefully emphasized yesterday, the denominator is really what makes this problem rational. That's just a fancy way to say that the denominator makes it a fraction. And so please make sure that this is something that you grab onto forever, that if there's a 0 in the denominator, if there's a number that gives you a 0 in the denominator, that's a bad number. And bad numbers show up in special ways. So x equals 6, plain and simple, is a bad number. It's going to be an asymptote. It's going to be like a number you can't touch. And we can be sure of that. Now the horizontal asymptote, how you doing with that? It's a set of rules. And look back at them or get to know them. Yes, eventually you memorize them, but it's basically just 3 situations. Make sure you understand what I mean by degree. The degree is the exponent. The exponent in the numerator is 1. The exponent in the denominator is 1. I'm talking about the highest exponent. So this is a classic case of the degrees are equal. It'd be like the middle option up there. That means we're going to use A over B. A over B would be like the coefficients. It would be, in this problem, 3 over 1. I can honestly ignore the minus 6, but I end up with 3 over 1. Now that seems to say that the horizontal asymptote's at 3, but I'll sort of share that that's not going to end up being the final answer. That's not going to end up being the final answer, but we'll come back to that. Okay? Maybe you're wondering if it has something to do with the +2. The answer is yes, for sure. Now the y-intercept is when you plug a 0 into the equation. And again, make sure that you're doing this, whether you actually write it out or whether you just kind of do it mentally. Now you'll notice that I'm plugging 0 into the equation, but just to mention, the +2 is part of the equation. So I got to kind of do like the whole thing. I got to do 0 over, well, it looks like 0 over -6. So you kind of figure that out, and then there's still this +2. Now know your math. 0 over -6 is 0. So it's 0 plus 2. 2. But plain and simple, I plugged into the equation. But of course, it's always tricky when you're plugging into a fraction. Okay? Nothing's, the next couple days, it's not going to be straightforward. It's not going to be simple because, again, it's a fraction. But work it out. Just like we're going to work this out, we're going to set the equation equal to 0. Now again, I'm setting the equation equal to 0. That's plain and simple, but I got to solve this thing. Okay? This isn't like an equation that we solved, last month, but it is an equation that we can solve for x. Let me help you out a little bit. You want to start kind of moving some numbers around. So I would subtract 2. Yes, the 2 is part of this. That looks a little bit closer to yesterday. Okay, yesterday we said multiply by the denominator. The only thing here is that when I multiply by the denominator, it doesn't just wipe out because -2 is going to distribute. Now we're getting a little more like an equation. -2 is going to distribute. Of course, that gives you -2x and +12. And now we're almost home free here. We can see that we're going to have 5x, and divide by 5 is going to give us 12/5. We did not see something quite like that yesterday, but I'll tell you that that's because of that +2. It made us do a little more algebra. So again, we get 12/5. Now, if I was going to put this stuff on a graph, which is kind of the idea, I would put this vertical asymptote at 6. So you've seen that a few times. I would plot these intercepts. Remember, I have an intercept at 2. That is 0, 2. So that can show up. Now 12/5, I'd have to understand if that's about 2 point, well, I didn't actually divide it, but it's 2 point something. So that's going to be somewhere in this ballpark. that'll be good enough. I can mark my 12/5 right there. Notice that I've left out the horizontal asymptote. That's because honestly, it's not right. But let's go to Desmos and see what we see. I appreciate, I know some of you have already typed this in, but let's give sort of a class view of this. And you'll notice that sometimes I'm zooming out, I'm sort of just backing off. Now, I feel like I see the vertical asymptote right here cutting down between these branches, and it is there. You know, you can actually type in x equals 6, and you can see the vertical asymptote. I didn't show you that yesterday, but feel free to do that. If I type in y equals 3, which is the wrong horizontal asymptote, I can see that it's not looking quite right. It's kind of cutting through here, and it needs to be in a different location. Now, what do you think the +2 is going to do to a horizontal asymptote? Can you see it visually?
Make it shift up.
Make it shift up is correct. Listen, that's always what a +2 does to an equation. It makes it shift up. Now, we perfectly land on 5. We land on y equals 5. So, what I guess I could have done, and I would say next time I would do, is I would see this +2 from the get-go, and I would know exactly what Chase said, that it's gonna shift my horizontal asymptote. So 3/1 was the right start, +2 is the right end, and again, I end up at y equals 5. Now, if you need to write something like that to yourself, I don't have like a big paragraph up on the screen, but if you need to say something to yourself like this is a vertical shift, but make sure you understand what it's going to affect. And I really want you to feel like a horizontal line is able to shift vertically. Again, a horizontal line is able to shift vertically. So it was at 2, it was at 3, but now it's up at 5. Look, this vertical line is not going to shift vertically. It's kind of silly to think about shifting that up and down. So it's going to affect the horizontal asymptote. Okay, don't forget, which looks like you guys are starting to catch on, we're trying to graph this daggone thing. So you got to draw the graph. You got to draw the branches. So the final answer is the graph with all the features and of course the branches. Is there anything else we can say? Is there a question? Remember, we're going to keep building on this today. So hang in there, have a good attitude, and we will get this. If you wanted to follow up a little bit with the homework, if you still have it handy, number 2 was a little tricky. Actually, I was impressed with how you guys went for it. A small detail is that the graph can cross a horizontal asymptote. Now again, that was something I mentioned yesterday, but it doesn't hurt to hear it again. I can cross a horizontal asymptote. It's not until I go to infinity. Now somebody says, well, where's infinity? Well, infinity is as I get to the ends of the graph. So as I get to the ends of the graph, then I approach the asymptote. But right here, that's not infinity. Same thing over here, I'm gonna approach the asymptote. Then we have this kind of this branch in the middle. Looks a little bit like your intro problem from a few days ago. Do you want to see anything with the algebra? Okay, the algebra for these numbers. I'm happy to, provide more.
Can you do the horizontal?
Sure, for number 2. Okay, honestly, it's just we're gonna just look at the numbers and we're going to say the degree is 1, okay, because it's x to the 1. the degree is obviously 2. Now when I see 1 over 2, when I see 1 compared to 2, it would fit into the first category, because the degree of the numerator is less than the denominator. Yep. Anything else? Are we okay with the y-intercept? Listen, I would plug a 0 in for both these x's, and I would just kind of get 5 over -4. Honestly, that's all there is to it. I can just say -5/4. You don't need to turn it into a decimal necessarily. All right. Well, let's continue. If you're taking notes, it's still really the same topic. Well, if you want to call it a 9.4b, if that helps you, but it's still basically the same topic. Consider means that there might be something you know about this, and there might be something that you don't know. And I'll say nicely that there probably is something that you don't know about it, because there's something new. There's something new, but don't worry, we can still look at x squared over x minus 6 using much of what we've already talked about. Are you okay if I abbreviate these sort of these lists of answers so we have referred to the last one code? Actually ends up being the same first last one code as the warm-up, but please start to be sure about that. X equals 6 is a bad number. Horizontal asymptote. Well, we just got a little review on that. Here's an example where the top is greater than the bottom. X squared versus x to the first. I don't think we've actually seen one of these officially, but if the top is greater than the bottom, that's the third scenario. That's an NONE, a big old none. Don't write 0. 0 would be different than none. What about the y-intercept? I keep showing this because I know that the y-intercept can cause trouble because it's a fraction. And anytime you plug in 0 into a fraction, you gotta be careful. Okay, so you kind of solve this in the warm-up with 0 over -6, that's legit, that's equal to 0. So I plugged in 0, I got 0. Well, that would mean that 0, 0 is our y-intercept. Now the x-intercept, if you're kind of catching on here, it would be the same thing, because 0, 0 is also an x-intercept. But I want to remind you that the x-intercept is what makes the equation equal 0. As we showed yesterday, you can multiply by the denominator, kind of just basically wipe it out. What you're really just staring at is 0 equaling x squared. If you were going to do the math, you would take the square root of both sides. It's a little overkill, but that's why you also end up with x equals 0. Now, it seems like, seems pretty simple, I suppose. We have an asymptote, we have an intercept. But there's more to it. There's a little more to it. To help see that, let's graph it. Now, if Desmos is so handy, you're more than welcome to graph it. I actually hope that you do. I'm going to graph this one on the graphing calculator. Graphing calculator is very similar to Desmos. You still have to use parentheses when you're thinking about the numerator and denominator. Kind of at first glance, it looks like, okay, we kind of get this graph, and Although it doesn't look quite like what we've seen before, it seems like it's approaching the asymptote. And in fact, it is. Now what I've done on my calculator is what's called zoom out. On Desmos, you can just scroll out. I kind of took a wider view. Again, if you zoom out or if you take a wider view, you can see that there's a little more to the branches. In fact, there's this branch up here, which you can draw in if you would like. But the reason we're really studying this problem is because there's another asymptote. Now, it's not another vertical asymptote because we already figured out the denominator. And it's not a horizontal asymptote because the rules said none. So what could it be? If it's not a vertical, if it's not a horizontal, you see another line that's acting like a boundary. How would you describe it?
A diagonal line.
Diagonal line. I'm doing my best to kind of put it in here. You kind of see it on your Desmos, you see it up here. And it's called a slant asymptote. It's a slant asymptote. Now maybe you're wondering, well, what is the slant asymptote? Well, it would have to be the equation for a diagonal line. Now remember what you've learned about diagonal lines. They're always y equals mx plus b. What's your favorite y equals mx plus b? Y equals x, somebody says. Or somebody did say. How's y equals x look? Seems like it's maybe not bad, but it's not right. How about y equals x plus 1? Gotta redraw, but okay. How about y equals x plus 3? Now, what I hope you're experiencing here is that it keeps getting better. Like, it looks like the slanted line is getting to fit. It's kind of fitting in where it's supposed to be. If you're not into guessing games, then I'll tell you it's y equals x plus 6. I want you to see the perfect fit. Now, if you want to type y equals x plus 6 in a Desmos, you can see it on your screen too. Y equals x plus 6 is the true slanted line. That's called a slant asymptote. And we can add it to our list. We can add it to our list. Again, it's called slant asymptote. It's an equation. It's the equation y equals x plus 6. I hope that you see it, but also hope that you're wondering, how did we get it? How did we get it? Well, it comes from division, because that's what a fraction really is. A fraction is really literally x squared being divided by x minus 6. And if you divide this fraction, if you, so to speak, divide it out, you'll find out what that fraction is trying to equal. I'm getting a little theoretical on you here, so bear with me. First of all, we have to divide out this fraction. So what do you mean divide it out? Well, I literally mean x squared being divided by x minus 6. In math class, we call that long division. Maybe there's a time where you wondered, why do we need to do long division? Here's the reason. Okay, now, what I'm actually doing is I'm finding out what this fraction equals. Okay, literally, I'm finding out what it equals to take x squared. Now, we need some placeholders in here, but to take x squared and have it be divided by x minus 6. Listen, you want to try to remember long division, but let's remember it. I always teach students that you really have to look at these terms and you just have to say, what do I multiply this x by to get this x squared? What do I multiply this x by? X. Now, I literally will multiply or distribute that x, which gives me x squared, that was supposed to be the same thing, and it gives us a -6. Remember when we talked about this, you have to subtract right here. But I always like to teach kids that that means you're actually changing the sign. You're subtracting everything. So I like to change the sign. And what do you multiply? You bring that at 0 if you want. What do you multiply this x to get this 6x? Well, of course, it would be the number 6. And then I multiply them. And if you would like, you can subtract. I say if you like, because you'll discover that you have a little bit of a rule coming here. This 36 is the remainder. The remainder can be written over x minus 6. Now listen, there's a lot of 6's, -6, +6, but this is like the whole number. This is like the non-remainder. This is your slant. The remainder ends up being what kind of pushes my graph away from the slant. So it's kind of like this. This fraction is trying to equal this. It's trying so hard. It wants to equal x plus 6, but it never will, because it keeps being added, it keeps being pushed away by this remainder. Okay, that's the theoretical reason why there's a slanted asymptote that is pushing the graph away, even though it keeps getting closer and closer. Now this is happening because the exponents are such that the degree of the numerator is exactly 1 greater than the denominator. Hear me out on this. This is happening because the top is exactly 1 greater than the bottom. Now, if the top is exactly 1 greater than the bottom, you're going to get a slant asymptote. And you can find it by dividing. You can find it by dividing. When you divide, you're basically looking for the mx plus b. You're looking for what it's trying to equal. And when it's trying to equal mx plus b, of course that will be your slant asymptote. Now we did open up another can here. Let's see if we can do at least one example, maybe 2. Remember, I'm not expecting that you're gonna get this in just one attempt, so keep listening. I'm actually purposely showing you a problem that has a slight difference to it, a slight difference. Yet, I hope you'll realize that it still fits into this category. We got 3x squared minus 2x plus 1 over x. Lovely fraction. And now speaking of that, that means that it's got certain behaviors. And what I'm getting at is that the list of behaviors, we just added. We honestly just added one. So we still have verticals, we still have horizontals, but now we're going to add slants. Of course, we still have the y-intercept and the x-intercept. Okay, so we're always looking for all the above or any of the above. That is where we're going to start with the denominator. Now, you haven't seen a denominator like this, but please don't let it fool you. That denominator has a bad number. It's already x equals 0. So x equals 0 is a vertical asymptote. Again, it's a bad number, I'm not allowed to equal it. Moving on to the horizontal asymptote. Well, you're probably going to discover sooner than later that because the top is greater than the bottom, now let's stop right there, because the top is greater than the bottom, there is no horizontal, but because it's 1 greater, there is a slant. So no horizontal, but yes to the slant. Now, it says up here that we're supposed to divide out the function. It doesn't say you have to use long division. Sorry if you're already setting up long division, I like that you're trying to keep rolling, but that's also division, to literally divide by x. It's actually a simpler form of division.
When you say is 1 greater, where are you getting that from?
Okay, remember,
What is
it's the degree. I'm glad you're asking, I should maybe show a little better. It's the degree. The degree is the exponent. So, I'm sorry, the highest exponent. So the degree is 2, the degree is 1. 2 is 1 greater than 1. Yeah, thanks for asking that. That's actually a good question. How's the division going? Did you realize that I'm basically just dividing everything by x? That means I can comfortably get 3x. That means I can comfortably get minus 2. Now, when I take the number 1 and divide it by x, well, that's the remainder. Okay, so this is a little different form of division, and it's because the denominator was simple, but it still fits. I get mx plus b. I get 3x minus 2. And of course, I'm going to ignore the remainder. How's the y-intercept? Plug a 0 in for x. This time I'm just going to point, because I can plug a 0 in there, I can plug it in there, but I can't plug it in there. I can't plug a 0 into this equation. Now, if you set the equation equal to 0, you encounter an interesting sort of phenomenon. That interesting phenomenon is that you have the numerator equaling 0, and the numerator looks like a trinomial. Now, trinomials can be solved sometimes with factoring, or maybe the quadratic formula. This time I'm going to tell you that if you use the quadratic formula, you're going to end up with an imaginary number. You're going to end up with the square root of a negative number. Okay, so if you haven't seen that yet, I don't want to spend a ton of time on it, but if you use the quadratic formula on the numerator, you end up with the square root of a negative. So what that means is that there's no x-intercept either. Don't make too many conclusions. Don't make conclusions like, we're not going to have any intercepts if there's a slant asymptote. That's not necessarily true. You have an intercept over here. It just turns out that we don't get an x or y intercept this time. What's this look like if you put it in Desmos? 3x squared minus 2x plus 1. All over x. Depends on sort of your vantage point. Looks like sort of 2 V's. Okay. Sometimes though, people like to graph the slant. Now, when I graph the slant here, it kind of sort of pushes itself in there. But the more of these you see, the more comfortable you get realizing that everything is fitting like it should. Now look, when I graph this slanted line, I really should graph it according to the y-intercept The y-intercept's -2, and the slope is 3. So, I kind of want to draw a line that looks like it has a y-intercept of -2 and a slope of 3. But the branch kind of squeezes in here. It's getting closer to the slant asymptote here. It's getting closer to the vertical asymptote here. And the same thing down here. At the ends of the graph, it's getting closer and closer to that do not touch line. Okay, I'm kind of at the same point yesterday where I don't want to squeeze an example in. Maybe I'll send you a link if you want to see another example, but tomorrow what we will do is we'll put brakes on and we'll practice this in class. I would like to ask you to practice it at home one more time. So of course there's a form over. There are some answers at the bottom. I hope that you use that to guide you a little bit. And like I said, we'll practice this tomorrow in class. Thanks for stopping by. I'm glad that you're taking a look at this last example. All right, thanks for stopping by. I'm glad that you're taking a look at this last example that we couldn't get at in class. It's a good rational function. The numerator is x cubed, 2x squared, x and minus 4, and the denominator is x squared minus 9. So, what do you think? Yes, it's a little bigger, but we can start with the denominator equaling 0. There's two ways to go about this. You could basically kind of solve it by adding 9 and taking the square root of both sides. Or, as I like to get students to notice, anytime something can be factored, then I recommend that you factor it. So x squared minus 9 very easily factors into x plus 3, x minus 3, which is still going to produce for us the same two bad numbers, that is 3 and negative 3. So I have vertical asymptotes at plus or minus 3. And notice that I'm writing it in the plus or minus form, which is fine. Now, if the horizontal asymptote is comparing the degrees, the degree of the numerator is greater than the denominator, and that's why we have no horizontal asymptote. But it turns out because the degree of the numerator is exactly 1 greater than the denominator, then we're going to have a slant asymptote. So are you ready to find the slant? You have to do long division. So to do long division, we have to set up the x squared minus 9 on the outside and the x cubed 2x squared, the plus x, and the minus 4 on the inside. Okay, well, as you go about this long division, you basically focus on these first two terms and you ask yourself, what do you multiply by x squared to get x cubed? And of course, that's x. Now when I multiply that, I'm going to have to line up the minus 9x with the like term. So when I do the subtraction, which really means I change the sign, the x cubes are going to cancel. The 2x squared is going to come down, but I'm going to end up with a 10x over here with those like terms. Now, did you see how that 2x squared came down? Because that's exactly what I'm going to look at in order to do my last part of my division. I'm going to have to multiply by 2. Now, I want to be honest with you, we're done as soon as we get mx plus b. Right now, we can say y equals x plus 2. I don't need to bother with doing any more division because I know I'm just going to get a remainder anyway. How about the y-intercept? Plug a 0 in for x. Now I'm going to do something because I have the technology here. I'm going to plug a 0 in for x, which means that everything except the minus 4 is going to become 0. And in the denominator, everything except the minus 9 is going to become 0. So look what I end up with. I end up with negative 4 over negative 9. Now negative 4 over negative 9 is the y-intercept, which basically simplifies to 4/9. 0, comma, 4/9. And lastly, if I'm going to set the equation equal to 0, if I set the equation equal to 0,
Well, I got myself a pretty complicated problem, because what that means is that the numerator has to equal 0. I'm not going to make you guys solve that numerator equal to 0. It's a polynomial, and it doesn't factor, and it turns out that the x-intercepts are decimals. So we're not going to worry about the x-intercept. Okay, we'll just kind of essentially cross it off or just kind of leave it blank. Now, to graph this problem, we want to be willing to mark and sketch these features. What features? Well, vertical asymptotes at plus or minus 3. So I'm going to go ahead and get some dashed lines positioned at plus or minus 3. What else? A slant asymptote at x plus 2. Now, x plus 2 is a line that has a slope of 1 and a y-intercept of 2. Can I draw a line that has a slope of 1 and a y-intercept of 2? Well, it's going to look something like that. And then we have this y-intercept at 4/9. If the y-intercept's at 4/9, it's going to be right around here. Now, you haven't seen a graph like this before. In other words, where we have all these crisscrossing asymptotes, but that's what Desmos is for. And so if you type it in Desmos, which I encourage you to do right now, you're going to get a graph that looks like this. Now, that's a good sign, because that graph is going to fit nicely into our features. I have this branch over here on the left, which is approaching the slant asymptote and also approaching the vertical asymptote. So that's good. I also have this branch up here at the top right, which is doing the same thing. Now, did you see that branch in the middle? Yes, there's a branch in the middle that kind of comes on down through here, and it does approach the asymptotes at the far ends, but it does cross the slant asymptote. Well, that's okay. You're allowed to cross a slant asymptote so long as it's not at infinity. And so it's a very common behavior for a graph to cross a slant asymptote in the middle. Now, you can put these asymptotes in Desmos by typing in x equals plus or minus 3 and by typing in y equals x plus 2, and you'll see the exact same features. You'll see the graph fitting nicely through those features.